Welcome to an exciting journey into the world of industrial automation. Imagine a factory floor where machines operate seamlessly, enhancing efficiency and precision. This is the realm of industrial automation, a critical component in modern manufacturing. It involves the use of technology to control and optimize industrial processes, reducing human intervention and increasing productivity. The importance of industrial automation cannot be overstated. It drives innovation, improves quality, and ensures consistency in production. As we dive deeper, you'll understand how advanced labs are revolutionizing the way we train the next generation of engineers and technicians. These labs provide hands-on experience with cutting-edge technology, preparing students for the challenges of tomorrow's industry. Programmable logic controllers, or PLCs, are the backbone of modern industrial automation. Think of them as specialized computers designed to withstand the rigors of factory environments. They are programmed to control machinery and processes, ensuring precision and reliability. Unlike general-purpose computers, PLCs are built for durability, operating efficiently even in extreme conditions. They communicate with sensors and actuators, making real-time decisions to optimize production lines. Understanding PLCs is crucial because they are the linchpin in automating repetitive tasks, enhancing efficiency, and reducing human error. As we dive deeper, you'll grasp how these devices are programmed, the types of languages used, and the best practices for integrating them into complex industrial systems. And here's why that matters. PLC programming software is the cornerstone of industrial automation. It's where you translate logic into action. This software allows you to write, test, and simulate your PLC programs in a virtual environment. Think of it as the command center for your automation projects. You'll need to familiarize yourself with its interface, understand the syntax, and learn how to debug your code. The software typically includes a graphical interface for designing ladder logic, function block diagrams, and sequential function charts. It's crucial to know how to navigate these tools effectively. For instance, when you're working with ladder logic, each rung represents a logical statement. Understanding how these statements interact is key to successful programming. Additionally, the software often includes simulation features that allow you to test your program without risking damage to actual machinery. This is where you can fine-tune your logic and ensure everything works as expected before deployment. Configuring your PLC programming environment is crucial for effective automation development. Begin by selecting the right software platform. For instance, Siemens TIA, Rockwell Studio 5000, or Codesys are industry standards. Once selected, install the software following the manufacturer's guidelines. Ensure your system meets the minimum requirements to avoid performance issues. After installation, launch the software and navigate to the New Project section. Here, you'll specify the PLC model you're targeting. This step is vital as it configures the environment to match the PLC's capabilities and limitations. Next, set up your communication parameters. This includes selecting the correct communication protocol, such as Ethernet/IP or Modbus, and configuring the baud rate and timeout settings. Remember, a baud rate of 19,200 is commonly used for legacy devices, while modern PLCs might require higher rates. Finally, establish a connection to your PLC. Use the IP address or serial connection details provided by your PLC documentation. A successful connection is indicated by a status change in your software, typically from disconnected to connected. This setup ensures your environment is optimized for PLC programming, allowing you to focus on developing robust automation solutions. Now, let's dive into the execution phase of PLC programming. Imagine your PLC program as a set of instructions that a highly efficient worker follows to automate tasks. The code logic is the blueprint, and the wiring is how you connect these instructions to the physical components. Start by defining your inputs and outputs. For instance, if you're controlling a motor, your input might be a start button, and your output is the motor itself. Next, write your logic using ladder logic or structured text. A typical ladder logic rung might look like this. If the start button is pressed, Then energize the motor. Ensure your wiring matches your logic. Connect the start button to the input module and the motor to the output module. Remember, precision is key. Incorrect wiring can lead to malfunctions or even safety hazards. Always double-check your connections. And here's a pro tip: use descriptive tags for your inputs and outputs to make troubleshooting easier down the line. To ensure your PLC systems run smoothly, let's dive into troubleshooting and optimization. First, when you encounter a system malfunction, start by checking the error logs. These logs are your first line of defense, providing specific error codes that point to the problem's origin. For instance, error code 101 typically indicates a communication failure between the PLC and the HMI. Next, verify all connections, especially the power supply and communication cables. Loose connections are a common issue. If the problem persists, consider the scan time. If it's too high, your PLC might be overwhelmed. Reduce the complexity of your logic or increase the PLC's processing power. Additionally, optimize your code by minimizing the use of complex functions and using efficient programming practices. Remember, a well-optimized PLC not only performs better but also extends its operational life. Keep these tips in mind, and your PLC systems will operate at peak efficiency.